I'm Chris Cunningham with the Institute for Transportation Research and Education at North Carolina State University. I'm going to share information on a recent presentation we made at the Transportation Research Board's summer meeting conducted by the Traffic Signal Systems Committee. The topic to be addressed by the committee was improving the double crossover diamond interchange, or DCD, through interchange and corridor improvements. Our team used Missouri 13 as a case study for this project. Several participants are responsible for the findings presented in this presentation. First, ITRE research staff are responsible for many of the findings at recently constructed DCDs in the U.S. through a federal highway research grant. Second, NC State's Dr. Joe Hummer, a leading expert in the field of alternative intersections and interchanges, is the principal investigator for this ongoing federal highway research grant. Last, Kimley Horn's staff led the effort on signal timing and geometric improvements discussed in this presentation. Before I get started, I'd first like to acknowledge our project sponsor, the Federal Highway Administration, who allowed ITRE staff to work on the current research grant titled Field Evaluation of Double Crossover Diamond Interchanges. Without the support of Federal Highway Administration, many of the findings presented herein would not be documented. Second, I would like to thank the Traffic Signal Systems Committee for providing a forum to challenge our profession to look at various improvements that can be made to the DCD and surrounding corridors. It was extremely interesting to see the various alternatives presented at this conference. As mentioned earlier, the objective set by the committee was to provide an improved DCD design and evaluate the operational improvements at the DCD and surrounding intersections along the corridor. Although the specific DCD interchange to evaluate was not provided by TRB or the Traffic Signal Systems Committee, our team chose the first DCD interchange constructed in the U.S., Missouri 13, as a specific case study. The project team was particularly interested in improving on the field observations at the first 7 sites studied under the ongoing FHWA research effort. At the time of this presentation, 14 DCDs were open or nearly open to traffic. The 7 sites studied extensively by our research team are shown with red stars. 3 common problem areas were evident at nearly all of the DCDs studied. These included spillback and metering of closely spaced intersections, extensive queuing from right turn movements on freeway off-ramps, and persistent red light running issues at DCDs where high cycle lengths were used at 2-phase signals. Specific examples are provided on the following slides. The first problem at almost all sites, especially the more congested DCD arterials, is the location of adjacent intersections. Although this problem is not new to interchanges, it is exacerbated at the DCD. This is because the DCD operates 2-phase signals, which are more efficient than the conventional diamond interchange. This means there is more available capacity at the 2 signals located at the interchange. However, the capacity at the nearby upstream signals provides a considerable choke point. The above example is from Lexington, Kentucky during the PM peak hour and provides a very simplistic example of the problem. The colors denote vehicles starting at one of the 3 westbound approaches of the 3 respective intersections. The primary movement during the PM is the westbound movement, as traffic comes from downtown to the suburbs just west of the interchange. As traffic begins to peak, the westernmost signalized intersection, shown in red, begins to queue up significantly. As the downstream DCD intersection, shown in blue, releases on green, it stacks in the queue at the upstream 8-phase signalized intersection. To further complicate the problem, the second downstream DCD intersection, shown in yellow, also releases. Obviously, the upstream 8-phase intersection to the west causes severe problems along the corridor, not allowing the DCD to operate efficiently as it was intended. Although the upstream signal is certainly a common problem, the downstream signal prior to the DCD is just as important. Again, using Kentucky as the example, the 8-phase signal prior to the DCD intersection starves the interchange by metering traffic. The available capacity at the interchange is not fully utilized, which leads to long queues prior to the interchange at this signal. In the leftmost picture, the queue is shown on the opposing side of traffic leading into the DCD. The picture on the right shows a view from the rear of this queue. This queue was approximately 1 mile or more in length during the peak. This presentation looks at ways to eliminate signal phases at the upstream and downstream intersections by geometric improvements in signal phasing strategies, all which ultimately improve progression along the arterial. A second key problem area is the right turn at the freeway off-ramp. The reason this is problematic is because most DCDs do not allow the right turn to turn on red. This is done for safety reasons because drivers tend to look down the wrong approach when looking for gaps, since they don't expect through drivers to be on the opposing side of the road. Seen here are two examples from a couple of DCDs we collected data. When the predominant movement came from the freeway in the AM or PM, this was a very typical scene at almost all of the DCDs we studied. Three different scenarios for the right turn off-ramp are provided on this slide. From top to bottom, the DCDs represented are Kentucky 4 at Harrodsburg Road, Missouri 13 at I-44, US 129 at Bessemer. The first two options do not allow right turn on red because of the close proximity of the right turn to the main intersection. However, the middle picture, Missouri 13 at I-44, later installed a second free-flow right turn in the northwest quadrant to the zoo to eliminate some of the traffic queuing issues. The last picture provides an alternative not considered or possible at the first two sites. A free-flow right turn movement well away from the main intersection can provide a safe maneuver. Obviously, right-of-way is a concern here, but even the possibility of channelizing a right turn with an acceleration lane could provide similar operation. The geometric considerations for the right turn that should be considered are moving the right turn ramps further away from the main intersection, adding a free flow right turn lane. If so, can you extend it through the next signal for additional capacity? It is important to consider the weave if a heavy left turn movement at the next upstream signal is prevalent, as shown with a red arrow at Kentucky 4 and Missouri 13. If an acceleration lane were added or right turn on red were allowed, this weave will present a safety concern that you will more than likely need to address. Some possible considerations could be to add a U-turn further upstream of the intersection and even possibly eliminating this left turn movement altogether. As discussed earlier, the upstream and downstream signalized intersections cause considerable spillback and metering issues. In addition, red light running was observed at many of the DCD interchanges being currently studied. The research team believes the primary link to this problem is the long cycle lengths that are used in coordination with adjacent signals. The two options we recommend for reducing signal phases, and thus cycle lengths, are geometric and signal phasing improvements to eliminate unnecessary phases, thus producing better progression opportunities. Possible geometric considerations include conventional and alternative intersection designs. The most common conventional design is the leftover, not shown here, but it is often used to remove or reduce the need for left turn phases at the main intersections by allowing some traffic to enter development at an upstream or downstream median opening. In addition, several alternative designs should be considered as they all reduce the need for signal phases at the primary intersection, thus increasing throughput on the main line. The most common of these designs are provided on this slide for reference, and each has applications that work better than others. The FHWA Alternative Intersections Informational Report, or AIIR, is a great reference for more information on these designs. Last but not least, several signalization strategies could be used to provide increased throughput along the main line. Several are considered for this case study. First, there are some locations where protected phases can be eliminated altogether or moved to an up or downstream U-turn opening or leftover. When possible, we use the permissive phases where protected phases exist, but only when this makes sense and there is no prominent safety concern. Split side streets are typically considered as a safety improvement. However, they can also be considered when a low volume approach exists at one of the side streets, allowing the phase to be skipped when no traffic is present. When using split side streets, be careful to consider if pedestrian crossings are present or heavily used. Flashing yellow arrows should be considered as they provide greater flexibility in phase order by using lead lag operation, or for shortening or skipping protected phases when possible. The interchange used by this team is the one located at Missouri 13 in Springfield, Missouri. It should be noted that this interchange was chosen by the team because it is likely to be familiar to the vast majority of the transportation profession. In no way does this case study indicate that this interchange and the Missouri 13 arterial are deficient or not operating as anticipated. Instead, the interchange serves as a case study by which the three problem areas mentioned earlier can be addressed in a systematic way, similar to many other DCDs that will be designed and constructed in the future. The corridor provided in this slide represents 4 signalized intersections. The 2 intersections located at the DCD interchange are operated by a single controller and are shown as a 3-phase operation in a single ring of a controller. This operates in a manner consistent with 2 two-phase signals if 2 controllers were in operation. It should be noted here that the signal phasing strategies are different at the DCDs currently constructed. These findings will be provided in the FHWA research report in the very near future. However, a similar presentation on that topic is forthcoming. The southernmost intersection is located at the main entrance of a Walmart, while the northernmost intersection is located at a Lowe's Home Improvement on the west and a zoo to the east. This is very typical of many busy interchanges where large commercial developments are located. Note that the 2 external intersections operate 6 and 8-phase intersections, while the DCD basically operates 2 two-phase signals. In answering the problem statement provided by the committee, our objective was to provide maximum throughput while minimizing queues at all intersection approaches. Our team accomplished this objective by focusing on reducing phases at adjacent intersections of the DCD through geometric improvements and signal phasing strategies. Although not necessary, we provide separate signal controllers at the DCD intersections, allowing viewers to easily view the signal phasing at the DCD. First, we will discuss the upstream and downstream intersections of the DCD. Provided on this slide is the current phasing scheme for the northernmost intersection at the Lowe's Home Improvement and Zoo. Currently, this intersection is operating as a 6-phase intersection with 4 possible mainline phases and 2 side street phases. Several problem areas exist. First, to promote increased bandwidth, we recommended reducing the number of phases by eliminating unnecessary movements, usually left-turn movements only, but through movements were considered also. For this particular intersection, the team recommends constructing a U-turn opening to the north of the intersection. We then recommend eliminating the westbound side street left and through movements and redirecting them to this U-turn. In addition, northbound lefts would no longer be allowed a direct left turn at the main intersection, but would also be redirected to this U-turn opening. The southbound and eastbound lefts would be allowed at the main intersection because the construction of a U-turn opening to the south is not possible due to its close proximity to the DCD. These geometric improvements would turn one 6-phase signal into 2 signals operating at 2 and 3 phases each, making them much more efficient and easy to coordinate. Provided on this slide is the current phasing scheme for the southernmost intersection at the Walmart. Currently, this intersection is operating as an 8-phase intersection with 4 possible mainline and side street phases respectively. Obviously, this is a considerable choke point that needs addressing. To increase bandwidth, the team recommends using the upstream northern entrance between this main intersection and the DCD as a leftover. This leftover would reduce the necessary demand from northbound left-turning vehicles into the Walmart. The current southbound left turn demands are very low into the Golden Corral located to the east. Therefore, permitted left turns are all that would be necessary at this intersection along the main line, provided a signal phase for the main line traffic. In addition, the team recommends using split side streets. The westbound through and left coming from the Golden Corral has very low traffic volumes and could therefore be skipped the majority of the time. Therefore, the eastbound through and left would be the primary side street phase being utilized. In short, this intersection now operates as a 2 or 3 phase intersection instead of the sluggish 8-phase intersection currently in operation, providing significantly more progression opportunities. The northernmost intersection of the DCD is shown here as a 2-phase signal. These 2 DCD signals are shown with separate controllers as signal phasing is more easily understood for the purposes of this presentation. Although not shown in this schematic, the westbound off-ramp has a heavy right turn movement causing significant queuing during the PM peak. One exclusive right turn was designed to go into the zoo. However, the other right turn is not allowed to right turn on red. The team recommends considering this as a channelized right turn with an acceleration lane that extends well beyond the next upstream signal at the Lowe's Home Improvement facility. The single most problem with allowing this free flow movement is the driver wishes to turn left at the Lowe's now have an unsafe weave. However, remember that the team recommended removing this direct left turn access at the main intersection just upstream. Therefore, the weave is virtually eliminated as all drivers now go to the upstream U-turn location. This slide shows the signal phasing at the southernmost intersection. This signal operates in a similar manner to the northernmost DCD intersection. No special considerations must be made at this time. The reduction of signal phases along the arterial allows significant improvement to be had. First, the cycle lengths are dramatically improved and offer much snappier signalization along the arterial. Also, the significant red light running problem observed at many of the DCDs currently in operation should be remedied with these shorter cycle length times. The time-space diagrams for the northbound and southbound movements, shown in red and blue respectively, are provided to show the improvements in progression along the arterial. Those not familiar with time-space diagrams in synchro should note that the southbound vehicle trajectories are aligned across two diagrams, while the northbound vehicle trajectories can be seen in entirety on the leftmost diagram. Two major points of emphasis are the improved bandwidth and reduced queue lengths at the signals. In fact, queues are practically non-existent. Similar findings are had during the PM peak, with only slight queuing at the 4th Lowe's intersection in the northbound direction of travel, denoted as red vehicle trajectories with approximately 14 vehicles per lane nearing the right turn off-ramp. As noted earlier, the right turn at this westbound off-ramp has significant problems releasing. We therefore recommend the channelized turn lane with a continuous lane through the next intersection to allow additional capacity at the upstream intersection located at the Lowe's Home Improvement. As part of this project, we were required to evaluate the corridor level improvements. Using synchro, intersection delays improved. In fact, intersections were projected to operate at level of service B or better at all approaches. Our team appreciates you taking the time to view this presentation. If you have any questions about DCDs, we'd be happy to entertain those. In addition, please take time to view our other presentations as they are released, or better yet, view any one of our papers or publications on DCDs that will begin to be published in the near future. ITRE's website is a great resource for research on DCDs. We would be happy to provide you access to those should you ask.